Right, this is on inverses of exponential functions. So you're given several values and we need to determine whether that's log, exponential, or neither. So it works exactly well opposite. So exponential, I think we know that just have to make sure that if the x is increasing with the same value, and if the y is increasing with the same proportion, then it is an exponent. For example, that's what is happening in question 1. The x is increasing with the same value, which is going up by 3, and this is increasing with the same I don't think so this is increasing with the same proportion. I thought it is, but no, actually, because 4 over 1 is 4, so this ratio is 4, but 9 over 4 is just 9 over 4. 16 over 9 is just 16 over 9. So this is definitely not exponential. Okay, here I think that's happening because it's going up by 1, and this is going this is being multiplied with 4, because 1 times 4 is 4, 4 times 4 is 16, 16 times 4 is 64. So this is definitely exponential in nature. Okay, now in log, exactly opposite happens, as in y increases with the same value. You can see that it is increasing by 2, while the x increases by the same proportion. So you can see that 1 times 2 is 2, 2 times 2 is 4, and 4 times 2 is 8. If that happens, then it is a logarithmic function. Okay. Likewise, here I can see that y is increasing or decreasing with the same value, in this case -1. And here also x is changing with the same proportion because it's getting halved, right? 40 over 2 is 20, 20 over 2 is 10, 10 over 2 is 5. So this is also a logarithmic function. Here we are given the graphs of two functions f and g, and we need to find the inverse. We need to graph the inverse. The reason why they have given this dotted line, and the dotted line is actually a y equal to x, it is because that the function and the inverse are actually reflection of each other about the line y equal to x. So that's the reason why they have given this to us. But anyway, a good way to graph inverse from its function is take some points and swap the x and y, because that's what we do in domain and range. For example, and the points that are, for example, I mean, take any point. I don't really see any nice grid intersection except 0, 0 comma 1. So 0 comma 1 will change to 1 comma 0, and 1 comma 0 is right here. And likewise, we keep doing this for other points as well. For example, this point looks like, I don't know, somewhere a little more than 2 and a little less than 3. So this, when reflected, will become a little less than 3 and a little more than 2. So it will probably somewhere here. In other words, I mean, the reason why I said reflection is because you can just drop a perpendicular actually to the other side. For example, if I want to find the corresponding point of this one on the other side, then you drop a perpendicular to y equal to x and then extend it with the same length over on the other side like this. So this will become your new point. Likewise, you can keep doing like this for all the points. So that way you will get this sketch that should look, for example, this point will now come somewhere over here and so on. So the sketch is going to look something like this one, right? This is going to be the graph of the inverse function. Okay, likewise, we can do here as well. Maybe we can start with this point, endpoint. So this is like about -4, maybe a little less than -4, and this is 6, right? Now the x coordinate will become 6. X coordinate is 6 over here, and the y coordinate will become -4 point something. So -4 point something is probably somewhere over here. So when we reflect, then this point is going to come right here. 0 comma 1 we know will become 1 comma 0, so it is right here. Maybe take any in between point as well. Let's take probably this point, which is -2 comma about 2, -2 comma 2, around 2. I'm not interested in the exact, I'm just getting an approximation. So this will become about 2 comma -2. About 2 is somewhere here and -2 is somewhere here. Okay, little more than 2, right? So this is Probably this is how the point is going to look. And finally, if we notice here, when x is approaching infinity, y is approaching 0, right? So in the inverse, when y approaches infinity, x will approach to 0. So where is infinity? Positive infinity is right here. So it will y-axis will become vertical as I'm told. So its function or the inverse actually should look something like this. This is how the inverse is going to look, right? Uh, all right. Now we have to use these graphs to approximate the following value. So this is a little interesting. Log of 3 with base a. So log of 3 with base a, since the base is a, we can see that it has to do something with the a raised to x curve, right? Now, let's say when I'm saying fx is equal to a raised to x, and fx is nothing but y, so we have y is equal to a raised to x, but I need log somewhere. So I need to take log with base a both the sides. So it will become log with base a of y is equal to log with base a of a to the x. So this will become log with base a of y is equal to x. And what should this y be? It should be 3, right? Because that's what I need to find. So replace y with 3 now. So this will become log with base a of 3 is equal to x. So all you have to do is look at the y coordinate of 3 on this curve, which is right over here, and figure out its corresponding x value. So this is 3 and they are asking us to approximate. So 3 is right here and here the x coordinate is somewhere over here. So it looks like between 2 and 3, maybe 2.6 around. This is 2, this is 2.6, approximately 2.6. So I'm going to say that my answer is 2.6 over here. This is for 7. Likewise, you do the exact same approach with this. I don't think so you need to do all these steps again because we can just borrow this step and right away say that uh, y is being replaced with 1 over 2 in this case. So log with base a 1 over 2 is equal to x. And where is 1 over 2? 1 over 2 is 0.5. 0.5 is right here. At 0.5, we go towards the x. So that looks like this, which is, I think, 2.5, right? Negative 2 and negative, between negative 2 and negative 3, it is negative 2.5. So I'm going to approximate this value as negative 2.5. Likewise, you're going to do the exact same approach, but this time with b. The approach is not going to change except that the a will be replaced with b. So I'm just going to write it over here that we are looking for log of y with base b is equal to x. The y should be 4. The only difference is we should now look at the other function. So if it is 4, where is y 4? Right here. So at y equal to 4, I can see that the corresponding x value is negative 3.5, right? Because this is negative 4. So this value is approximately negative 3.5. For log base b4 is approximately negative 3.5. And then we have question number 10 where this is 3 over 2. 3 over 2 is 1.5. 1.5 is right here. If we go 1.5, at 1.5 I'm getting negative 1 around. So in the log with base b of 3 by 3 over 2 is approximately negative